Today we'll see the various network elements which we'll be using in circuits. The first one is resistor. Resistance is property of a material by virtue of which it opposes the flow of electrons through the material. And 1 ohm is defined as the resistance offered by the material when a current of 1 ampere flow between the two terminals when 1 volt is applied across it. So when you apply a voltage of 1 volt across a resistance, and if the current flowing through the resistance is 1 ohm, then the resistor is current is of 1 ampere, then the resistance is said to be 1 ohm. Now, in order to derive the equation for voltage developed across resistor, we'll start with the basic Ohm's law in electromagnetic form, which we have already learned. J equal to sigma E, where J is current density, sigma is conductivity of the material, and E is the electric field developed across the material. Since J is current density, you can write it as I by A, which is equal to sigma into electric field is voltage by length of the conductor. So I by A equal to sigma into V by L. From there we can write V equal to L by sigma A into I. Now here length of the conductor is constant, conductivity of a material is constant, and area of cross section is constant for a given temperature. So R is constant for a given temperature. R equal to L by sigma A. So we'll get V equal to R into I, or V equal to IR, which is the Ohm's law in circuit theory. So related to circuit theory, if you are asked to state Ohm's law, that is voltage equal to I into R, where R is constant. Now here I have shown a circuit where a voltage V is applied across a resistor R, and I is current flowing through it. As discussed in the previous class, a resistor can always absorb power only, it cannot deliver power. So in presence of an active source V, the resistor will absorb power. That's why I have marked it as plus and minus. The current entering terminal of resistor will always be positive and the leaving terminal will be negative. Now these are the equations which you will have to learn with respect to resistor. V equal to I into R. From there we can write I equal to V by R. Power is product of voltage and current, which is I squared R or V squared by R. And energy is P into T, which is I squared RT or V squared by RT. These are the basics of resistor. Next we'll see capacitance. Capacitance is the ability of an element to store electric charge within it. A capacitor will store electric energy in the form of electric field established by the two polarity of charges on the two electrodes of a capacitor. Quantitatively, we can say capacitance is a measure of charge per unit voltage, and the unit of capacitance is farad. So capacitance is said to be 1 farad when 1 coulomb of charge can be stored with 1 volt applied across the two electrodes of the element. So we say that the capacitance is 1 farad when 1 coulomb of charge can be stored when you apply 1 volt across it. So if Q is the amount of charge that can be stored in a capacitor of capacitance C, against a potential difference of say voltage V, then the charge stored is directly proportional to V. The charge stored in the capacitor is directly proportional to the voltage applied across it. Or you can remove the proportionality sign with a constant C, that is Q equal to CV. So this is a basic equation governing capacitance. Charge directly proportional to voltage. So Q equal to CV. Now we have learnt in the first class that current is rate of change of charge with time, or I equal to dq by dt. Now Q here is C into V. C is a constant. So we can write I equal to C into dV by dt. So current flowing through a capacitor is C into dV by dt. Now when we observe this equation, we can see that if the voltage across a capacitor is 0, then there is no rate of change of voltage with respect to time, right? So dV by dt will be 0. That means the current flowing through the capacitor will be 0. Or in short, current 0 means you can represent it by open circuit. So we can say that capacitor will act as an open circuit for DC. And now from that equation for current, I am taking dV on one side and all the other elements on the right side. So we will get dV equal to 1 by C into I into dt. Or from there we can write down equation for voltage developed across capacitor, V equal to 1 by C integral I dt. So we have learnt three basic equations. One is Q equal to CV. Then I equal to C into dV by dt. Then V equal to 1 by C integral I dt. Now from there we can write down the equation for power. The basic equation is voltage into current. So here current is C into dV by dt. So we can write P equal to Vc into dV by dt, or V into C dV by dt. Now I am rearranging this slightly in order to find out the energy. Vc dV by dt can be written as d by dt of half CV squared. Now when you perform that differentiation, 2 and 2 will get cancelled and you will get the same equation back, which is V into C into dV by dt. So power is rearranged as d by dt of half CV squared. So that energy is integral P dt. So the d by dt will go off and you will get as half CV squared. So the basic equations governing in capacitor is Q equal to CV, I equal to C into dV by dt, V equal to 1 by C integral I dt, power equal to Vc dV by dt, and energy is half CV squared. Now we see that if you plot a graph with a voltage across x-axis and charge developed across y-axis, we will see that it is a linear graph, right? C is constant, so we'll get a linear graph with slope equal to C. So capacitor is a linear bilateral passive component. Now I forgot to mention this graph with respect to resistance. Now if I plot voltage versus current, again here also you will see that the slope is linear. I will get a linear graph with slope equal to R, or R equal to V by I, and here C equal to Q by V. So this is all about capacitance. Next we will see inductance, denoted by L. Inductance is property of a material by virtue of which it will oppose any change of either magnitude or direction of electric current passing through the conductor. So whenever there is a change of either the magnitude or direction of current, inductor will oppose it. Inductance is said to be 1 Henry when current through a coil of conductor changes at the rate of 1 ampere per second, inducing 1 volt across it. Okay. So, when a time varying current is flowing through a coil, a time varying magnetic flux will be produced. So, this flux is denoted by psi. Now, this total flux produced in the coil will be proportional to the current flowing through the coil. That is, psi is directly proportional to current flowing through the coil. Now, you remove the proportionality sign and replace it by a constant which is L. So, psi equal to Li. Similar to what we have learned in capacitance where Q equal to CV, here it is psi equal to L into I, where psi is the total flux produced, I is the current flowing through the coil. So from there we can write down the voltage drop across the coil, which is V equal to d psi by dt. Substituting for psi, we will get V equal to L into di by dt. So voltage developed across a coil of inductance L is given by V equal to L into di by dt. From there, we can write equation for di equal to 1 by L V dt. From there, we can write down equation for current flowing through the coil I equal to 1 by L integral V dt, or power equal to V into I. Substitute for voltage developed across the inductor, which is L into di by dt. So, we will get power equal to Li into di by dt. Similar to what we have done in the capacitance case, we are rearranging it and writing the power as d by dt of half Li squared. So that energy stored in the inductor is half Li squared. So the basic equations for inductance to be memorized are psi equal to Li, voltage induced across inductor, L into di by dt, current 1 by L integral V dt, power Li di by dt, and energy half Li squared. Now similar to what we have seen in capacitance and resistance, you can draw a graph with flux versus current. You will see that the graph is linear with slope as L. So this is the basics of inductor. Now let's see series combination of resistance. Now consider a circuit where Rn resistors R1, R2, R3, etc. Rn are connected in series and a voltage Vs is applied across it. So we can see that when many resistors are connected in series, same current will be flowing between all the resistors, and the voltage, the total voltage will divide among the different resistors depending on the resistor value. So the value of VR1, VR2, etc., VRN will depend on the value of the particular resistor. More the value of the resistor, more will be the amount of drop across a particular resistor. So the total voltage Vs can be written as sum of the different voltage drop across the resistors. Vs equal to VR1 plus VR2 plus VR3 plus etc. VRN. Now I am writing it in terms of current. So Vs can be written as total current into effective resistance. So Vs is I into R effective, which is equal to VR1 will be I into R1, VR2 will be I into R2, etc. So the equation will be IR effective equal to IR1 plus IR2 plus IR3, etc. IRN. You can cancel I from both the sides. So we will get R effective equal to R1 plus R2 plus R3 plus etc. Rn, which is nothing but the sum of all the resistances. So when various resistances are connected in series, effective resistance will be sum of all resistances. Now we'll try to find out what is the value of voltage drop across each resistance. For that, we'll write down the equation for I. The total current I equal to V by R. So here it will be Vs by R effective, or here it is R total. What is VR1? VR1 will be current flowing through R1 into R1. That is VR1 is I into R1. I we have already written before. So I you can substitute, which is Vs by RT into R1. That is voltage drop across R1 equal to total voltage into R1 by total resistance. Similarly, VR2 will be I into R2, which is Vs into R2 by RT. So in general, we can say voltage drop across any arbitrary resistance Vrm equal to total voltage into that particular resistance by total resistance. This is a very important equation which you will be using out throughout in the subject. So please learn it clearly. Voltage, when various resistors are connected in series, drop across any one arbitrary resistance, say Rm, can be written as Vrm equal to total voltage applied into that particular resistance by sum of resistances. That is Vrm equal to Vs into Rm by RT. A very important equation. So this series combination of resistors is otherwise called as voltage divider circuit, because we have seen here when Vs is the total voltage, it gets dropped across various resistances, and the amount of drop will depend on the value of each resistance. So this is also called as voltage divider circuit. Now we'll move on to the next one, which is parallel combination of resistance. Here we'll see that when when resistances are connected in parallel, it's the current which divides between the various branches. The voltage will remain the same. So parallel connection means voltage will be the same. So now we'll try to see here what is happening. The total current I will split between the two branches. So we can write it as IR1 and IR2. So total I is equal to IR1 plus IR2. Now I am substituting for each current. I is the total current, so it will be the voltage applied V by R effective is equal to IR1 will be V by R1 and IR2 will be V by R2. You can cancel V throughout, so you will get 1 by R effective equal to 1 by R1 plus 1 by R2. If there were many resistances, say Rn resistance, you can write it as 1 by R effective equal to 1 by R1 plus 1 by R2 plus 1 by R3 etc. 1 by Rn. For a two branch network, we can write it as R effective equal to, by simplifying the equation, we can write it as R effective equal to R1 R2 by R1 plus R2. Now I am writing the individual current in each branch. IR1 equal to, voltage is the same, V by R1. Now V is I into R effective by R1. We have written out R effective already. So when you substitute it, the R1 term will get cancelled and you will get I R1 equal to I into R2 by R1 plus R2. Similarly, we will see the current flowing through the second branch R2. So it will be I R2 equal to V by R2, which is again substituting. You will get it as I into R effective by R2. Substitute for R effective. R2 term will get cancelled and you will get I into R1 by R1 plus R2. Again, these two, I R1 and I R2, are very important equations which you will use an infinite number of times in our future classes. So please learn it by heart. For a two-branch parallel network, current flowing through one branch is equal to total current into opposite branch resistance by sum of resistance. Please take it down. For a two-branch parallel circuit, current flowing through one particular branch is equal to total current into opposite branch divided by sum of the resistances. So, the current flowing through R1 will be total current I into opposite branches R2 divided by R1 plus R2. Similarly, current flowing through R2 will be total current I into opposite branches R1. I into R1 by R1 plus R2. So, these two are very important circuits. If it is a voltage divider circuit, the current flowing through it will be the same throughout. It's the voltage which get divided. If it is a current divider circuit, then the voltage will be same for all the branches. It's the current which get divided. So this is a very important topic which you'll have to understand and learn very clearly. Now we'll see the series combination of inductance. Consider two inductance L1 and L2 connected in series, across which you apply a voltage V, resulting in a current I flowing through it. As it is a series circuit, the voltage will divide among the different elements as V1 and V2. It's a voltage divider circuit, so the total voltage can be written as L into di by dt, where this L is the effective inductance. Since it's a series combination, it's a voltage divider circuit, so you can write V equal to V1 plus V2. V is L into di by dt. V1 is L1 into di by dt, and V2 is L2 into di by dt. So the equation will be L into di by dt equal to L1 di by dt plus L2 di by dt. Di by dt will get cancelled. So effective inductance L equal to L1 plus L2. So effective inductance is same as effective resistance. When connected in series, you just add up all the inductance value to get the effective inductance. Next is parallel combination of inductance. Here you can see two inductance connected in parallel. L1 and L2 are connected in parallel, and a voltage V is applied across it. Since it's parallel combination, current gets divided between the two branches. So I will be equal to I1 plus I2. I is, we have already learned, current flowing through inductor is 1 by L integral V dt. So we can substitute I equal to I1 plus I2, which is 1 by L integral V dt equal to 1 by L1 integral V dt plus 1 by L2 integral V dt. Integral V dt can be cancelled. So you'll get effective inductance when connected in parallel are 1 by L equal to 1 by L1 plus 1 by L2. Again same as that in case of resistance. Next we'll see series combination of capacitance. So we have two capacitances C1 and C2 connected in series, across which we apply a voltage V, resulting in a current I. Since it's a series circuit, the voltage will get divided among the two capacitances. So you can write V equal to V1 plus V2. V is voltage across capacitor is 1 by C integral I dt, which is equal to 1 by C1 integral I dt plus 1 by C2 integral I dt. Integral I dt can be cancelled, so we'll get effective capacitance 1 by C equal to 1 by C1 plus 1 by C2. That is, when you are connecting two capacitance in series, the effective capacitance will be 1 by C equal to 1 by C1 plus 1 by C2. Next is parallel combination of capacitance. You have two capacitances C1 and C2 connected in parallel. So here the current will get divided among the two branches. So if I is the total current, it get divided into I1 and I2. So you can write total current I equal to I1 plus I2. Current flowing through capacitor is C into dV by dt equal to C1 dV by dt plus C2 dV by dt. C1 and C2 will get cancelled and you can write C equal to C1 plus C2. So when two capacitances are connected in parallel, effective capacitance will be sum of the two capacitances. So this is about series combination and parallel combination of capacitance.